Let me just make sure this is going through. Perfect. So here's the plan today. I'm going to be live all day, minus breakfast and dinner, from now until probably like 8 p.m. Try to get a minimum of 10 hours streamed in. We're going to try to really clean up all of our training code for next release. And I think that today, compared to yesterday, we're actually going to start looking at more of the features that we currently have in place and deciding which ones actually matter and which ones don't. So pretty much anything that I haven't used in months, we will just drop. And there are a few things that I want to try out. I want to try out this distributional thing really quick. I think I might have been a little overeager to start on this yesterday. But since I got a little bit of progress in on it, I think I'm going to spend we'll probably give this like the first hour, hour and a half today. And if I make any progress, I make some progress. If I don't, I don't. And yeah, we will just continue from there. The first thing that I want to do, take a look at this run here. Is doing quite well. We will see how this does when it finishes. It's going to take quite a while. And then next, I want to take a look at the distributional Q-learning paper, because I want to see how Belmare and everyone does this. Now, it's not going to be one-to-one because this is for Q-learning. Okay, so they say skip this section. This is background. I believe they have the algorithm definition here. So this is a very simple distribution. They're just saying that you pick a minimum and a maximum value. You bucket your value function into n intervals uniformly over that. And then you take softmax over the outputs of each value head in order to get the probability of being in each bucket. Now, how do they actually sample this thing? I'd like to know. Okay, using a discrete distribution poses a problem. The Bellman update and our parameterization almost always have disjoint supports. Okay, I haven't seen enough of their math for that, but we'll come back to this. It would seem natural to minimize the Wasserstein metric between these, which is also conveniently robust to discrepancies in support. In practice, we're typically restricted to learning from sample transitions, which is not possible under the Wasserstein laws. Instead, we project the sample Bellman update onto the support, effectively reducing the Bellman update to multi-class classification. Let pi be a greedy policy. Given a sample transition, we compute the Bellman update, reward plus discounted ZJ for each atom ZJ. Okay, so this isn't what I was thinking. And then we distribute its probability to the immediate neighbors of this. Okay, this is not what I was thinking about. Or this is not how I was thinking about it. But I think it gets simpler in the on-policy case anyways. The ith component of the projected update is... The heck is this? Okay, so this is just reward plus discounted value. And then this is the bucketing operation. So this is them just doing really annoying fancy floor ceiling stuff, but this is, I think that this is just them bucketing the value function here. Okay, so it's good that I found this. They actually need like 51 buckets. That's a lot. The fact that this doesn't work at all on Sequest until you go to 51 is very sketchy. Yeah, I don't understand what this thing is doing here, though, at the bottom. So this loss is just... Wonder if this is in clean RL. It is. and it is quite short. Okay, so let's see the output of this thing. Okay, so it's n times the number of atoms. And that gives you the value. It gives you like this discretized value for each predicted action, which is going to be different from what we do in the online case. Okay, and now here we have potentially what we're looking for. You get actions, PMFS. Okay, so this is the probability mass function for each action, is what this is. And then this is going to only return the probability for the action that you actually take, I believe. Which is good because that's how we're going to do it in online case anyways, or on policy case anyways, so we should be really easily able to figure this out from here. So this is just our value function output, softmax of our value function output right here. And then they do next atoms, reward plus gamma times atoms. Yeah, now we have to figure out this mess here. So we have delta Z, target network dot atoms of 1 minus target network dot atoms of 0. Let's figure that out. I think this is the delta atoms. I don't see atoms here. Target network dot atoms. This is the only network they have. Register buffer. Okay, here, it's a linspace right here. So this is literally just going to be the step delta. So if it's like 0, 1, or 0, 0.5, 1, 1.5, then it's just 0.5. And then what are we doing here? We're going to clamp this to min and max. Okay. And then how do they set V min and V max also? Oh, these are arguments. Yeah. That's interesting. But they just set these to like big values. Okay. So those are just constants. If that's all it is, then that's actually not that bad. That's not that bad. I thought it was going to have to be some weird dynamic thing. So then we take B dot floor. Okay. Now the thing that's a little sketchy here, right? There's going to be a difference here between the Q-learning version and our on-policy version. So let's see what we have so far. We get the probability distribution over actions. Oh, this is... Yeah, so this doesn't depend on this at all. So this is just, this next atoms thing is just for every possible value that you could have, rewards plus discounted value. Okay, so then there's the projection. This still doesn't depend on this at all. And we don't depend on this at all until here. So all this is building the targets, I guess, right? All of this is just building the targets. And then this becomes, I believe this is just a categorical. Why are they... Okay, so you get your action here, and then the loss is your actions, or your log. This is your action log probs. I'm pretty sure this is just cross entropy. Yeah, I'm pretty darn sure. So this is just your action probability, or action log probs. It's a cross entropy from your action logits to whatever they've decided this target PMF action index is. So all of this is just computing an index. There's nothing fancier going on that I can see. So if we can figure out how they're computing an index and how we modify it specifically for on policy, we will be good. Hang on. This building was specifically constructed to avoid having sun glare. But my table is reflective. Okay. So what are they doing here? They're saying they take rewards plus discounted values. And then here is this delta. Who wrote this code, I wonder? Is this Costa's code? Some of it. Okay, so it's a little confusing because these are out of order here. But they are just clamping this, like, discounted reward thing between the min and the max. Then they apply this transformation. So I think they're splitting it between two adjacent buckets or something here. Ah, wait, is this too hot? L of I dot long. Okay, I don't understand this transform here. So you're normalizing. Wait. This is not depending on next PMFs at all, right? Yeah, no, this does not depend on next PMFs at all. It does depend on the rewards. So you're using the rewards to construct the targets. You're doing this like normalized, this reward minus discount value, whatever. This is a norm. And then you clamp this. You're getting two integers out of this. The floor and the ceiling. Like previous bucket, next bucket, something like that. And then it's a very fiddly operation. I'm having difficulty figuring out what the heck they're doing. Do you need to do this? Do they have ablations? Huh. That's crazy. This was accepted with a way higher mean score. But their median was correct. It helps on almost every game. Mhm. I actually don't know if we should really even do this right now because, like, does this make sense outside of the off-policy context? You learn the distribution. You don't know the action yet, right? It's not action conditioned. I think that the smartest thing to do with this, given that there's actually like some complexity here, and I'm not just implementing it one-to-one, it would have to be a modified version for on policy. I think we just stash this for now, and I mean, we see here though that the way I was thinking about P30 is completely different from this. It's going to be like ridiculously. Yeah, and then the way this is, the version of P30 I had in mind would become ludicrously expensive as well. Because this is now predicting. I mean, honestly, this alone is probably already somewhat expensive. Yeah, I don't want to just go do this wrong and like conclude that this doesn't work because there's actually like a pretty non-trivial modification. I think that this should be like on the top of the stack for after the update. This is something that I should look at here. But like the thing is that this is going to require quite some modification because like this is going to essentially require me to decide or to figure out the whole on policy versus off policy split that happened with what most of what DeepMind did and most of what OpenAI did in like late 2010s, early 2020s. So I think that's going to be part of the next research segment. So I don't think it makes sense to spend like another hour on this to do that. So here's what we're going to do. Pass. We're going to just remove all P30 stuff for now. We'll do the C++ later. Okay, we're at 1294 lines from that. We still have the vtrace experiments to do. So those we'll actually have to do the experiments on. And then there's the question of, can we get Diane to do anything as well? Let me see, what are the key questions we have to answer in order to, like, really get this thing to work? Project name, please. This is PufferLib. All my stuff is at Puffer AI. Whoops, not this one. Puffer.ai. And we have ultra high perf reinforcement learning M's. You can play them in your browser. You can take over. You can watch. This is me playing. If I hit control here, this guy will now be playing. We have everything from, like, simple arcade games, like this miniature version of OpenAI 5, and lots in between. This is really a comprehensive effort to fix everything wrong with reinforcement learning. Let's just, like, get a quick multi-M benchmarking, normalized score. I did that. We need, let's see, sampling methods for batch or replay. Form clip flags. Off policy. JE first vtrace puff. Did I miss anything? What other, like, options are there? So there's, like, this vtrace stuff. I guess optimizer choice. So, like, the difficult thing here is some of these, get rid of this. Some of these, we want to run, like, a bunch of experiments prior to release on these. There's a clip value loss and there's normalized advantage, these two. What else? We can do perf stuff on AMP and distributed today. That's a pretty easy one to conclude. The GAE V-trace puff advantage, that will be experiments. Diane will be, we need to run some experiments. Off policy has never worked. Welcome, Boxen. Get rid of this. Did you manage to get yesterday's stuff working? The PyTorch stuff I did, yeah. The distributional stuff that I started towards the end, I looked at again this morning. It's more complicated than I thought, and it's going to be like, that's going to end up being a multi-day thing, and I think that it makes more sense to do that once I have this release done as part of my next effort, which is going to be a lot of algo side stuff. What about this target KL? This is like something that it seems like we should use but don't, right? We can play with this as well. I kind of just want to like get rid of all the options and flags here. I don't want this to be like, oh yeah, you have the options to do whatever. Like, this should just be the best set of things that works. That's it. Done. And like anything that a question comes up, we will test it and we'll figure it out definitively. Okay, so we still have this working, 1271 lines, 3 million steps per second training. Looks good. There we go. Let's do, I think we can't do compile yet. We should be able to do AMP though. Why does this not have this? B float 16. So this still trains, but did it do anything? Float 32. Okay, so I must have messed this up at some point. Backward passes under autocast are not recommended. Okay. We're not going to leave it this way, obviously. The backward pass right here. And we can actually check we can check dev branch to make sure we do this right. So this is slower. Performs worse. Okay, so there is something here. What we should do, though, here, we're going to save this. Now we will reapply all this stuff. So, automatic mix precision is supposed to just be faster. It's supposed to just work everywhere. It's very possible, though, that there is something screwy with small models with it just being slower, but it's also possible that there's, like, some weird back-end set, and that I've just been doing it wrong. So that's what we're going to figure out today. Going to figure out if this is valuable, if this should be an always enable, or if this should be a toggle. So here's your float 32 training. This should work. And the actions has a D type, and this has its own D type. Cool. See if this still runs. Okay, this still runs. It's nice and fast. Float 16. All tensors must be float 32. Lovely. Is there any way around that? No, because it's in place as well. Yeah, that's sketchy. Hmm. Okay, so maybe I can't store it like this just yet. We should still be able to make it faster. If this works well, then I will consider making the kernel support multiple D types. Vote. Okay, so it's definitely slower. Let's see if it trains stable. Get out of here, bot. We train the bots around here. Okay, so this does still train. Potentially a very small drop. Maybe not at all. Yeah, it's about on par. But it is slower. Now, if I run with float 16, it is still slower. Is it stable, though? Seems to be. Let's see if we're actually doing what we expect here. Like, is this actually... Yeah, this is float 16. Okay, so this is doing what we expect. If I don't set this, it's redoing something. Running out of shared memory somehow here. Hmm. Ah. There we go. So this was actually screwing with something, it seems. What are you building? I'm working on PufferLib. This is ultra-high performance reinforcement learning library. We have lots of demos on puffer.ai. It's all open source, and I stream all the dev. I'm curious if B-float now gets faster all of a sudden. Now see, so B-float is still slow. B-float is still slow. Is that expected? I don't think that should be expected. So FP16 should be faster. Oh, this is lightning. Let's try a larger model. Okay, so this is original full precision. 450 is about right. Okay, so this is a little bit faster, not much. I mean, that is something, though. It's a pretty disappointing difference, though, for going to 16-bit. Oh, hang on. Now do we see the speed up from B-float? Yeah, no, we do see the speed up from B-float now, right? Okay, so that's actually worth considering. It's small. About 10%. But it's there. And that should let us optimize other stuff more, right? Because now... No, we actually have very little overhead on this either way. I think Neuralink on Discord has done quite some research on precision stuff. RL Discord, discussion Discord, maybe you could answer some questions. The old big RL Discord, is that still active? I guess the main question would be how much relative to what it has been. Yeah. I guess the main thing is like we see the speed up only on the larger models, and it's way less than we would expect, I think. And it's not like we see... Yeah, it's not like there's additional misc time or anything. This also could be... Hang on. I think there is actually... Do we do like float? 16. Or let's just do float 16. Ah. Let's see if this does anything different. Float 16. Maybe then we get the expected speed up. Okay, that's something, right? Yeah, now that's a reasonable speed up. So yeah, we have these casts in here, so you have to be very careful with your casts. How do you cast? Maybe it will auto cast. .2. So now we're getting the expected perf improvements. At least not the, well, not I wouldn't say the expected, but we're getting something substantial. And we get most of it with B-float as well. Cool. So now we see that this is a thing. Can we try it on like Snake, perhaps? This should be a fast env. Gonna re-optimize a bit. $2.8 mil. And if we go to float 16, tiniest bit faster. If we go to B-float, much slower. So worth using. We probably want to default this based on model size, I would guess. I'm trying to think why it should be slower. It's just like there's extra casts and stuff. I mean, it could be worth putting all the buffers into this format. Oh, interesting, the learning pass got slower. You see that? The learning pass got way slower. Okay, let's figure that out. Because maybe I did that wrong. Hmm. Can remove scalar if only using BF16. Let's see, you need grad scalar with BF16? Okay, so we don't need this. Still slow. So it's not the scaling. Very odd. Very, very odd. What if I do just the inference? Now what are we at? 25, 22, 23? Okay, so this is comparable. It doesn't help now, but it doesn't hurt either. Check neural MMO. Should be 450. Yeah, so you do want it on the backward pass. But for whatever reason, it's worse with Snake and with the smaller models in general. It can't be the comms, because Breakout doesn't use comms. This is 2.8. Okay, so very marginal. Yeah, there's something, but it's very marginal. I'm trying to think if there are any other M's I could play with for this. New meta. Does that work now? Yeah, I gotta equal to segments. Now we have this slice annoyances. Lovely. Okay, I just needed this for an extra test M, because this is like a very slightly larger model. Okay, so there's 500K. Okay, so that should be everything. And then nothing here. Okay. Interesting. Oh, this has env-perf issues. I see. That shouldn't have env-perf issues, so that's weird. Okay, so float 16 actually does help, though. So yeah, this is what I was looking for, right? Does anybody know what LLM people do these days? What are people doing these days for LLMs? Okay, so they're quantized. They're still trained on this. Okay. I had thought that maybe people had gotten lower precision training to work by now. So I mean, this does train here with FP16. FP16 non-tensor core has especially high throughput. Hmm. Very weird. I really would like to know why there is a perf difference. Because it makes it very difficult to benchmark stuff. Like, I'd really rather not have to have float 16 at all if I can get around it. There's definitely a speed difference. I wonder if it's hardware dependent. Yeah, these are supposed to be the same. Unless something is getting cached weirdly, right? But it would have to be doing this in every single one, which is unlikely. Let's try Pong. Make sure I don't see any out of memory errors. Okay. So there's Pong. Pong is ridiculously fast. 4.7, 4.8 mil. Cuts the perf in half immediately. In float 16, is slower. Slightly. That could just be the additional data cast, though. I mean, I guess it's something like the cast has to be unoptimized or whatever, because you do get the performance in bigger models. For bigger models, the B float and the float is about the same as well, right? If I do like neural MMO3, well, I've already tested this. It's about the same. So I don't even really think we want to mess with FP16 as much. Like, do we really want to guess? I don't really think we want to guess at stability issues being like from FP16. But I think for now, well, how hard is it to write your kernel with FP16? It also, maybe we don't have to do it in place. Okay, maybe I don't have to write the custom kernel here. Maybe we'll do, here, let's do this. Move this for now. I know what we're gonna do. Whoops. Is it 9:51? Okay. Lost track of time. I will be back right after breakfast. And then we will finish AMP and we will keep optimizing this stuff. So thanks, folks. Puffer.ai for all the things. Start the GitHub to help us out. Come join us on Discord if you want to get involved with dev. And I will be back